Welcome back. In this last segment, we're going to put together the insights from the previous segments to provide an intuitive justification, if not a formal proof of the master theorem. To make this discussion easier, we're going to stay with our usual assumption that n is a power of b. Of course, the master theorem still holds if that's not the case, but this assumption makes the picture easier to understand and the justification more intuitive because it makes the tree symmetrical with all the leaf nodes at the same level. So at level 0 in a generic recursion tree, then we have one node, the root node. And then at the next level we have a few more nodes, and then we go down until we hit some random level, level I. And what happens at level I plus 1? Well, of course, at level I plus 1, there are more nodes than at level I, because the number of nodes grows by a multiplicative factor a from one level to the next level down, as we argued before. So we keep going down the tree until we reach the leaf level, which has even more nodes. Remember, more than half or the vast majority of the nodes are in the leaf level, and that level is level k. Notice it's not a coincidence, this is the same k. K is log base b of n. Remember, we already argued that the number of levels under the root node is equal to k because that's the number of time it takes starting from n dividing by b each time until you reach 1. So our final goal here is to compute the total runtime of the algorithm. And for that, we're going to do a few intermediate computations, which now should be pretty straightforward given the previous discussions. So first, we're going to record the input size at each level in the tree. At level 0, or the root node, the input size is by assumption n, this n, and then the input size is cut down by a factor of b every time we go down to the next level. So at the next level, the input size is n over b. At the next level, it would be n over b squared. So what is the input size at level I? Well, it's going to be n divided by b to the power I. Similarly, at level I plus 1, the input size is n divided by b to the power I plus 1. And finally, at level k, the input size is n divided by b to the k, that is 1. That's the base case of the algorithm. That was the assumption, remember, that in our analysis, the base case of the algorithm happens when n is equal to 1. Now let's focus on the runtime of this algorithm. First, we're going to look at the runtime at each node in the tree, the runtime per node. Well, we know that runtime is on the order of n to the power d, where n is the input size. And in fact, the input size is equal to n at the root level, so the runtime for this one node is n to the power d. Now, of course, at the next level down, each node has an input size of n over b, therefore the runtime at each one of these nodes is n over b to the power d. And so on and so forth for each level after that. So take this number, raise it to the power d, and you get the runtime at each node at level I. Same for level I plus 1, all the way down to the leaf node. Now remember, at the leaf level, level k, the runtime is just a constant. So let's use constant 1. Notice we haven't bothered with the multiplicative constant here. We just use 1 in the theta notation. So this is just the order of the runtime at each node. So now we're going to consider a whole level at a time. We're going to compute the runtime for a whole level. Well, since every node in that level has the same input size, therefore the runtime for each one of these nodes is the same. So all we need to do to compute the runtime for the whole level is to multiply these numbers by the number of nodes at each level. And we already computed the number of nodes at each level. Let me write them down again. Remember, we multiply by A every time we go down each level. So, what is then the runtime per level? Well, it's just the product of the number of nodes at that level times the runtime per node at that level. So at level 0, we have the product of n to the power d times 1. At the next level, we have this number times a, and so on and so forth. Let me just fill in the column now, just by multiplying the two previous columns. Now, notice we have a pattern emerging, at least in the middle rows here, since a is the same as a power 1, b is the same as b power 1, and you notice the pattern is that every term in that column is the product of a number to the power d, where that number is a fraction of n. It's n over b to a power that keeps going up by 1, and the second term in the product is just an increasing power of a. So it looks like the exception to this pattern is the first and the last level. But actually that's not the case. We can easily fill in the blanks. So notice that 1 here is equal to a power 0. So let's put that back in. Of course, n is equal to n divided by 1, and 1 is equal to b power 0. So we can replace this n with n divided by b power 0. And now you can see that this expression follows the same pattern as the ones below it. And similarly here, we can replace this empty term, which is just 1, by n over n. And notice n is equal to b power k, so we can replace 1 by n over b power k. And since n over b power k is 1, 1 power d is also 1, so we don't change the value at all. And now the pattern should be pretty explicit. So finally, we're ready to discuss the solution to this recurrence relation, that is, the function f of n, that is the runtime of the divide and conquer algorithm for an input of size n. While the runtime of the algorithm is nothing but the sum of all the runtimes of all the levels in the recursion tree. Now, instead of computing this sum to get the total runtime, let's take a different approach and let's compare the runtime between two consecutive levels. What we want to see is the runtime bigger at this level or at that level? Or is it the other way around? So let me call the runtime at level I RT sub I. And that runtime is equal to this expression. So I'm going to rewrite it a little bit differently here. Notice we have n to the power d times a to the power I divided by b to the power I times d, which is exactly this expression here. Now, let's do the similar rewrite for the runtime at level I plus 1. So let's take this expression for the runtime and rewrite it in a similar way. Notice that these expressions are extremely similar. So what we want to know is, how does the runtime change when you go from level I to level I plus 1? Does it go up? Does it go down? Does it stay the same? Well, the only difference in these expressions is that I becomes I plus 1. Everything else is the same. So what does that mean in terms of the overall value of the runtime when you go from here to here? Well, we go from a power I to a power I plus 1. That is, the runtime is basically multiplied by a when we go from level I to the next level I plus 1. Now, the other thing that happens, let's not forget, is that we also have b to the power d here. So b to the power d goes from a power I to a power I plus 1. And because b to the power d is in the denominator, when we go from this level to this level, we are really dividing by b to the power d. And these are the only two changes in the runtime from level I to level I plus 1. And finally, you see why in the master theorem we compare the value of a to the value of b power d. That's because these two values drive the runtime of the algorithm by determining how the runtime changes from one level in the tree to the next. Now we are ready to consider the three cases of the master theorem. The easiest case, case 1, is when a is equal to b power d. So what happens to the runtime here? If you multiply by 1 and you divide by the other, and both of these numbers are equal, that means you're basically changing nothing, which means the runtime at this level I is the same as the runtime at level I plus 1. Now, of course, these formulas hold for any level from level 0 to level k, which means the runtime is the same for every single level in the recursion tree, in that case only. Now, what is that runtime? Well, since all of these expressions return the same value, we can take the easiest one to compute, which is, remember, the product of 1 times n power d. So the runtime at each level is on the order of n to the power d. Finally, what is the overall runtime of the algorithm, f of n? Well, f of n is on the order of the runtime at each level, which is n over d, times the number of levels, which is what? Well, the number of levels is k plus 1. And k is the log base b of n. So k plus 1, we can just approximate that with k. As n gets bigger, k gets bigger, and the plus 1 doesn't matter. So the number of levels is on the order of log n. Since the runtime for each level is n power d, the overall runtime is the product of n over d and log n. And that is indeed the result of the master theorem in that case. The next case of the master theorem we're going to consider is when a is less than b to the d. So what happens to the runtime when we go from level I to level I plus 1? Well, we're multiplying by a, but we're dividing by a greater number. So overall, the runtime goes down from level I to level I plus 1. And so what happens in this case is that most of the runtime is concentrated on the first level, because every time we go down one level, the runtime goes down. In other words, the overall runtime of the algorithm is dominated by the runtime at level 0. And what is the runtime at level 0? Well, we already computed that. It's on the order of n to the power d. And again, that is the answer of the master theorem in this case. When a is less than b to the power d, f of n is on the order of n to the power d. Finally, the last case is when a is greater than b to the power d. So what happens is you're multiplying the runtime at this level by a number a, and then you're dividing by a smaller number. So overall, you're multiplying by a number that's greater than 1, which means the runtime at level I is less than the runtime at level I plus 1. In other words, the runtime increases as you go down the tree, which means the overall runtime is dominated by the runtime at the leaf level, RTK. Now, what is the runtime at the leaf level? Well, it's just 1 times a to the power k. So in other words, in this case, f of n is on the order of a to the power k. Now, this looks a little strange because this runtime does not seem to depend on n. But of course, that's an illusion, because remember, k is equal to log base b of n. So let's replace k by that value, and we get a to the power k is equal to a to the power log base b of n. And it's important to remember one of the properties of the logarithmic function, which is, in this case, we can swap the n and the a while keeping the b unchanged, which means this expression is nothing but n to the power log base b of a. So in other words, a to the power k is equal to this expression, which means that f of n is on the order of n to the power log base b of a. And again, that is the result of the master theorem in this case. So this concludes our informal quote-unquote proof or justification of the result stated by the master theorem.